kan gitu ya. Musim basahnya nih hujannya berlanjut hingga Mei. Padahal kan bulan puasa bulan pembakaran dosa ya. Biasanya kemarau tuh. Ini hadisnya yang salah atau data lo yang salah? Baca dong hadisnya. Setiap bulan Ramadan itu kemarau. Kenapa? Karena ada pembakaran dosa. Panasin dulu. Soal nanti menjadi hujan lagi itu soal nanti. Tapi kalau begini kan kondisinya, ini hadisnya perlu dipertanyakan nih, sahih nggak nih?
Oh,
Ya,
let's.
canda-canda.
Selamat sore Bapak Ibu semuanya. Selamat.
Mana nih Pak Moderator?
Oke, ini dia Pak Moderator.
Pak Moderator sudah hadir.
Ngomongnya di session ini ada orang bulenya nggak sih?
Ya, English kayaknya.
Ya, English. Alright.
Eh,
Ada satu orang Bapak,
Sopo?
Paul Davis,
Paul
Mr. Paul
Davis.
Davis. Alright.
Ya,
Sorry, Simon Pittman. Simon Pittman.
ya udah enggak, maksudnya 1 lawan 7 ya kalah lah satu. Lebih jelas gitu.
Ya.
Nggak apa-apa sih.
Oke, so jadi kita sepakati saja in English mungkin ya Bapak ya, karena
Oh iya.
ada dari native. Alright, good afternoon, ladies and gentlemen. Welcome here.
Udah mulai gitu.
Ini
Cek.
just I think we will check the presenter first
Iya.
and the conference. After that we can start.
Kaget akunya.
And first of all, maybe I will check from the presenter. So based on the schedule, the first one is Mr. Harrison Primadonna. Are you there? I think Mr. Harrison is not already here.
I'm here.
Oh, thank you very much, Mr. Harrison. And for the next one, we have Mr. Adi Ripaldi. And good afternoon, Mr.
Yes, good afternoon.
Yeah,
Amir.
have a nice day. And the next one is Mr. Simon Pittman. Are you here, Mr. Simon?
Yes, hello, can you hear me?
Okay, so are you in Leeds? So I think, yeah, still in the morning in there.
It is, yes, it's 9 o'clock in the morning.
All right, yeah. Have a nice day. We will check another one. Okay, after that we have Alif Nabilatur from ITB.
Yes.
Yes. All right. And the next one is Rigita Putri. You can speak in here for check the sounds. And Rigita Putri Damayanti. Rigita, okay, I think still not here. And so we will move to Firas Rashad. Mr. Firas?
Yes, I'm here.
Okay, thank you very much for the confirmations. And then the last one is Devi Fatmasari from BMKG. Miss Devi?
Yes, I'm here.
All right, so we just lost one presenter. And I think we can just start now because the time is up and we have a little bit late from the plenary session. So I think we can start the oral presentation now. So welcome here, the Honorable of the Convener, Professor Dr. Eddie Hermawan and Dr. Kunio Yoneyama. Are you here, Mr. Eddie is already here?
Yeah, I'm here. Nice to meet you again, all participants. Welcome to the session.
Thank you very much, Mr. Prof. Ed. And the next one, for the convener, we have Dr. Kuneyama. Isn't already here? I think not really. Hello, Dr. Kunio Yoneyama. Are you have been here? I'm not really sure. I think Dr. Kuneyama is still not here. Yeah, so we can start now because we have the controller here, and maybe we we will waiting the Dr. Kuneyama and just start the presentations. Is it always 12:80?
For me,
Yeah, or should we have
okay.
wait for Dr. Kuneyama?
Okay, ladies and gentlemen, good afternoon for all of you. Welcome to this important session. We talk in the basic science, and here we have how many?
Seven presenter here.
Seven presenter. We would like to see what you have done, what is the important point you will be talk in this session. And now still we are waiting for the Dr. Yoneyama. Maybe we should ask him in Japanese. Yoneyama-san, imasenka? Sorry. I hope you all can give best your presentation with good motivation and good result of then we hope you can make presentation at in time 10 minutes or 12 minutes, and then the session will be lead by Dr. Amir Mustafa from BMKG, and please enjoy this afternoon meeting in this session, and hopefully we can find some nice, interesting find result of the
pipeline system. Millions of dollars are lost and mining production is dropped. 2008, and some mining operations suffered a great loss due to flood and storm that happened in Queensland. Heavy rainfall in early June 2012 caused the artificial banks on the basin of Mulberry River across the Yolan mine to collapse. And as one of the largest oil production in Indonesia, Bojonegoro has the same potential loss due to extreme rainfall phenomenon. Bojonegoro Regency is situated in the inland part of the northern Java Plain on the banks of the Solo River, the longest river in Java. Bojonegoro also become a new focus attention Indonesia after a new oil field found in this area. This oil field is the biggest discovery in Indonesia in the last 3 decades and one of the biggest oil rivers in Indonesia. And the characteristic of its partial and temporal rainfall variability is high because long-term deterministic rainfall forecast is impossible. Rainfall is one of the nonlinear meteorological parameters which possess high variability data. This may explaining why rainfall prediction is such a difficult process to be done. Rainfall forecasting is one of the most difficult parts and is still under forecast study. Several studies have been successfully improved the accuracy of prediction on any weather parameters such as temperature, pressure, and wind, but it did not occur in rainfall forecasting. Meanwhile, rainfall forecasting plays a significant role in certain sectors, such as mining operation. In this case, treating rainfall as a chaotic system is appropriate way. This method may create a better understanding the underlying dynamics. And the aim of this paper is to analyze chaotic behavior of rainfall series data by using maximum diagonal exponent and determine optimum prediction time of rainfall occurrence to perform better weather forecasting, especially in the petroleum mining sites in Bojonegoro. Okay, the next method. The data we use is come from rainfall observation posts near the mining sites in Ngampatelo village, sub-district of Tender, Bojonegoro, East Java province. We use daily observed rainfall data for the last 6 years between 2012 to 2017. The rainfall data then processed into 3 different temporal scales, mainly daily, 5-day, and 10-day. And the methods is the studies beginning by determining the time delay. Time delay is chosen as optimum delay, where the model information takes on the first minimum value. This value is used for the best representation in the base case. In this research, the time delay is determined using average model information. And the second is estimating embedding dimension using false nearest neighbor methods. And after we get the time delay and embedding dimension, we can reconstruct the base space. Base space is a necessary condition for calculating maximum Lyapunov exponent for the time series. And finally, we can analyze the chaotic behavior on rainfall in Vajanagara based on Lyapunov exponent and determine the optimum time prediction. And this is the method we choose to determine time delay using average model information or EMI using the following equation. And this is the equation for estimating embedding dimension. Lyapunov exponent is used to recognize the dependency of system into its initial condition and show the dynamical behavior of the system. This value is also to use to determine the predictability of system. And the following is the equation we use to determine the maximum Lyapunov exponent. Okay, the next is the results and discussions. The corresponding figure A, B, and C solve for the value of EMI varies of the time delay in different temporal scale, A for daily, B for 5-day, and C for 10-day. The time delay for the space reconstruction is the first minimum value. This value is time delay corresponds to the optimum time delay for calculating the Lyapunov exponent. The range of time delay for each temporal scale for daily, 5-day, and 10-day rainfall series is 3, 2, and 3 days consecutively. And the modified algorithm of tau that applied to all rainfall time series data to identify the total embedding dimension, and after the calculation process, it's known that optimum embedding dimension in study adopts as for all temporal scale. And then this is the maximum Lyapunov exponent. And maximum Lyapunov exponent for daily data is around 0.11. For 5-day temporal data is around 0.057, and for 10-day temporal data is around 0.062. This exponent in all temporal scale in this study is greater than 0, indicating the daily rainfall series in Bojonegoro undergoes chaotic behavior. And then we can determine the optimum time of prediction rainfall using this equation, Ts divided by lambda max, where Ts is the temporal scale. And for daily temporal scale, it could be recognized from the optimum time predictability for rainfall prediction is 9 times than the temporal scale for day in daily. It means that the daily rainfall forecast will be optimum to predict within 9 days ahead maximally. If it is over than 9 days, the result of the prediction or forecasting will not good enough. Meanwhile, for 5-day and 10-day temporal scale are 18 times than the temporal scale and 16 times than the temporal scale, respectively. The results of study can be used to improve the accuracy of weather forecasts by simulating most effective time forecasting patterns. In other words, weather prediction could not be better than above computed predictability horizons.
You have 2 minutes more.
Okay. The last is conclusion. The one is maximal exponent for daily, 5-day, and 10-day respectively are around 0.11, 0.57, and 0.62 respectively, with the positive value indicating the Celtic effort or rainfall in Bojanegra. And the optimum time of rainfall variably for daily, 5-day, 10-day are around 9, 18, and 16 times longer than temperate scale respectively. And understanding the optimum prediction time of rainfall occurrence may result in better performance of rainfall forecasting, especially relative to the effort improving accuracy value. Well, that's all my presentation. Thank you for your attention.
Okay, so thank you for the presentation. So for the audience that have a questions, please just write down the questions on the chat box so the presenter can answer the question at the end of the session. Okay, so we go next to the second presenter. It's Miss Noriska Lukita. Are you already in the Zoom meeting? Okay, I think she's not here yet. So we can just go to the next presenter, Mr. Wendy Harjupa from the National Institute of Aeronautics and Space, LAPAN. Please, Mr. Wendy.
Okay, thank you very much, Pak Donaldi. Very good afternoon, ladies and gentlemen. Pak Donaldi, Prof. Edwin, let me share my PPT. Oh, my voice is clear or not? Can you hear my voice?
Yes, very clear.
Yes, clear.
Thank you very much. How about my screen?
Yes, we can see.
Okay, thank you very much. Okay, today I want to present our research about the utilization of Himawari data for heavy rainfall prediction and its verifications. So this research belongs to LAPAN, Andalas, University of Andalas, ITB, and BMKG. Okay, let me start with the background of this research. This disaster was flash flood disaster, which occurred last year when the Boys and Girls Scouts was away by the flash floods in Jakarta. At the time, about 257 junior high school was away, and 4 among them died. So at the time, we know that based on the information of the media, no clear indication or no warning, and of course, because of that, we need to develop the early warning system for this kind of the disaster, and to design to to develop the early warning system, we need like a high temporal and high resolution data. So this is just a model of the one single convection, one single cumulus cloud. Let me start by the maybe from the turbulence, and then the cloud cure, and the next time we have rain particle inside of the cloud and continuously become very heavy rainfall and dissipation. Actually, for the nowcasting, for the certain prediction, in Japan, it's been started by Nakakita, Professor Nakakita. Since 2010, they use the radar, so the rain radar, to detect the inside of the cloud, the first echo of rainfall. They call it as the baby rain cell. So this baby rain cell should be developed as the very very heavy rainfall. Then the inside of baby rain cell should be has a vorticity. So this is detection by radar. By this research, Nakakita et al. Found that they can predict the occurrence of heavy rainfall 20 minutes before the first rain detected by rain gauge. Not before the heavy rainfall, but before the rains detected on the ground, because we have time between the radar detection in the space to rain detection at the surface. So there is a time. So to have more time, more early time to prediction for how to set for very heavy prediction. So Sumit et al. From JMA, Japan Meteorological Agency, already started to use Himawari data on 2016, and Wendy et al. Continues this research 2018. So we try, because the Himawari has like bind temporal and spatial resolution data, we try to find the behavior of clouds, what clouds moving before the heavy rainfall. So Wendy et al. Found that about by the verification in Japan area, we found that the average time, the first time we can detect 30 minutes by using the Himawari data. So for simply, I want to say that Himawari just can detect the clouds, surface cloud from the above. Because this is a Himawari, because this is passive sensor, it cannot detect the lower level cloud or the second cloud, just take the behavior of cloud at the surface. And then we have radar here to detect the first echo of rainfall in the space, because the rain radar only can detect rain particle. So rain particle, not cloud particle. So rain radar cannot detect the cloud, just it can detect the cloud, not rain. So this is the how to use the rain radar, and then we can verify by using rain gauge and Parsifal. So this is data and instrument data. Of course we use the Himawari data, but we have because in this the next research of my research after Japan to apply this concept in Indonesia, we have challenge, because in Indonesia we don't have such a fine temporal and spatial resolution. Because in Japan, maybe they have like 500 meters for visible bands and 2 kilometers for infrared. But and temporal is about 2.5 minutes. And it is very nice to see the cloud behavior, the cloud movement, development. But Indonesia, we just have like 4 kilometers spatial resolution and 10 minutes. But this is challenge, how to apply this concept in Indonesia. Well, we just use, among the 16 bands of Himawari data, we just use 7 bands, and we combine these bands to be certain parameters. So these certain parameters, all of these certain parameters indicate the cloud development. Actually, if we have like fine temporal and spatial resolution data, based on this, image, we can see the, after 10 minutes in the cloud development, we can see, of course, the cloud top is higher. In one grid data, the cloud top is higher than other clouds. This is how Himawari data can detect the cloud development. And of course, if the, if there is cloud development, should be the cloud roughness, we have the cloud surface more coarse. And then of course, in the cloud development, the pace of clouds, the water pace should be changed to the ice pace. So these three indication we can obtain from the certain parameters. So this is again certain parameters that we can obtain from the Himawari data. Maybe yeah, we have visible infrared data and also detection of ice cloud by this BTD concept. I mean, this is a common. I mean, for how to say it, the people use the satellite Himawari data. And how we use the certain parameters. So JMA, Japan Meteorological Agency, already developed the RDCA model, RDCA concept. These are the concepts how said adopt the logistic regression approach, logistic regression model. We certain parameter is much with the lightning data in 1 hour. So the behavior of cloud by using such parameter is much by the lightning data in 1 hour. So why we use lightning data? Because lightning data, I mean, coincident occurrence with the heavy rainfall. This is an assumption. So we match the data, then we can get the logistic regression correlation. And of course, we have here like A0, A1, we have like logistic regression model that we can generate the prediction of the heavy rainfall.
You have 2 minutes more.
Okay, thank you very much. Sorry, this is the result. This is the result. Just this is combination of one band of Himawari data, band 13, with the RDCA. RDCA means the RDCA index, which generated by the RDCA model. As we can see here, of course, the TV we can see the cloud development, but the RDCA can show the same pattern. So why we use the, why one band cannot predict the occurrence of heavy rainfall? Because, for example, band 13, if we find the lowest temperature of brightest temperature, maybe this can mean like common CV clouds, but also can be cirrus cloud, because cirrus clouds also occur in the high level. Also give the same numbers, lower value of brightness temperature. But here we use the combination of band to see where whether the we can predict the the heavy rainfall. So next, this is the simply sample, the simple of the example. Maybe we have two lowest brightness temperature here, and as we can see here, this number maybe around value is about 240 Kelvin, but we just have, by using RDCA index, we just have like one area that can predict the heavy rainfall, and we can, we verify by using radar data. Then we can see here, we don't have like 2 or 3 place of the prediction of heavy rainfall. And also the second sample, we have like here the very lowest temperature here, and also not so, like same like 240, but this can we can see that this by using RDC index we can see, in the not so low brightness temperature value, RDC index can predict, it should be, by using this model we can predict that maybe the heavy rainfall will occur at this place. As we can see here, this is the verification by using radar data. And this is just a sample, like a flash flood in Jogja. Because of the time, I just want to say simply that maybe by using this one, we also can, from the 12 o'clock, we already see the signal of the occurrence of heavy rainfall in Yogyakarta. So this is...
The time is up. Can you just go up to the result, to the conclusion?
Okay, just conclusion. We have like RDCA can be used to predict the rainfall, and also we can use the RDCA index not for only for convection. I skipped the sample, but I check. Whether the RDCA index can predict the the early morning precipitation, which always occur in Jakarta in February. Okay, thank you very much, Pak Donaldi. Everyone, I'm sorry for taking time. Thank you very much.
Thank you, Wendy, for your presentation. Okay, so I would like to welcome Dr. Ahmad Faki. He will be one of our convener as well. Okay, so we can go to the next presenter. It's Miss Hanifa Nur Rahmadini from the MKG. Are you in the meeting room?
Yeah, I'm here. Can you see my screen?
Yes. Yes, I can see. Yes, please. Time is yours.
Okay. Good afternoon, everyone. Thank you for this opportunity. My name is Hanifa, and I would like to present our paper entitled Early Warning of Accident Pollution Using Time-Like Acceleration System, case study in February 15, 2019. This presentation contains 4 parts. The first is introduction, methods, result, and discussion, and the last part is conclusion. Part 1. Various methods are developed to maximize numerical weather prediction models in making any type of weather forecast, including issue and early warning. The method that is currently being developed is using statistics and combine them into ensemble prediction system or EPS. This interflow between statistics and EPS will provide better prediction of extreme weather based on model characteristics. The system also claims to be able to predict the extreme event at least 216 hours or 9 days before the event. So that's why this research is focusing on using statistics, especially percentile, and combining them into time-like ensemble. The advantage of using models with different initial times, such as in time-like ensemble prediction system, is simply a combination of past prediction and recent prediction, so the system is able to detect various possibilities along the way to the predicted time. This research is conducted by the idea of whether or not the percentile classification method in time-like ensemble prediction system is able to predict properly heavy rain in the case studied. Second section, method. This research is conducted on heavy rain case that happened in February 15 around Bogor area. The main data used in this research is integrated forecasting system data or IFS, originally from ICMWF. On period December 2018 to February 2019. IFS has spatial resolution of 0.125 degree and 3 hours of temporal resolution. One IFS member has an estimated period of 240 hours and also using estimated data per 3 hours in observation. The step of conducting this research is described below. First of all, we are extracted the value of every grid around Jakarta and Bogor area, approximately 63 points in each lead time. And then we categorize them into 2 places, which are 90 percentile and 95th percentile. We choose the 90 percentiles because according to Matsueda and Nakazawa in 211, this percentile commonly used as the upper limit or the extreme limit of model extreme precipitation parameters. And according to Zhang and Yang in 2004 and also Siswanto in 2015, the 95th percentile is when the total rain is categorized as very wet days. And then both percentiles is defined as extreme threshold and used in the 73 and 1 days prediction. After we getting the extreme threshold and we are forecasting the main event divided in 3 categories. The first is intensity, location, and also probability. This sim is adapted from Mittermeier in 2007. It's showing how we construct an EPS, an ensemble of forecast initiation cycle from top to bottom with a 3 hours of time span and time-like ensemble with different initial times from left to right. The darker color show the longer lead time and the lighter color show the most recent time. A complete time-like ensemble is shown by the inside of the red box in this figure and which contain a time slices of various initiation times. Section 3, result and discussion. On February 15, 2019, rain observed at several points at around Bogor. The highest daily rain accumulation was at Citeco Meteorological Station with a total of 87 millimeters and Dramaga Climatological Station with a total of 56 millimeters, and both of them are considered in the extreme category according to BMKG in 2010. As we take a look here, rain intensity exceeds 20 millimeters per hour at both stations occurred around 16 to 17 UTC. This indicates that the rain originates from the same convective cloud and it is in a fairly broad cloud coverage. And then we begin to processing IFS data processing. We were extracting 63 points around Jakarta and Bogor. to study the characteristic of model itself. The model performance looks quite good in this study because at lead time 12 to 54, the average value and standard deviation tend to be the same. This is indicate that this is the highest model skill and in this data training. At lead time 60 to 144, average value is decreases and standard deviation is increased, indicating that the model uncertainty is raised. This is the result of each percentile around research area. They show a similar pattern. The mountainous area, such as Bogor, having a higher threshold than coastal area, such as northern Jakarta. But as evidenced by the fact that each grid has its own threshold value, even though in a nearby location, the threshold value is almost the same in both percentiles. So this is the forecasting, which show how many lead times we combine on every complete system in the ensemble. Blue box showing a complete slice of day 1, 3, and 7 of early warning issue. This is the threshold we using. There are several points around the case or around the main point as we considered as the extreme threshold because we were choosing the lowest value to anticipate any possibilities. This is the result of 7 days before the event in February 8. The predicted average rainfall in Bogor range from 2.5 to 5 millimeter per 6 hours at 12 UTC, and in the 90% probability on 7 days before the cases it reaches 20%. Meanwhile, the 95th percentile only reaches 10 to 20%.
You have 2 minutes more.
Okay. The 3 days before the event in February 12 is almost the same, but with increasing average value of precipitation. Although the location is not currently precise on the event, but the probability on both percentile is reaching up to 40%. 1 day before is exactly on February 14. Is extreme rain even reaching 20 millimeters per 6 hours. The center of the highest precipitation is shown a fairly precise location at Citeco Medical Station, and both percentiles shown above 80% of probability. This is the result of the intensity threshold based on data training, and the results show in the forecast. Meanwhile, the probability thresholds are adapted from Black and Milne in 2004. Using 90 and 95% threshold has a very good pattern from 7 to 1 days of prediction time. So consistency is always increasing in these cases. Overall, this forecast is show a quite consistent pattern because it is known that the pattern, the prediction pattern in mountainous areas such as Bogor is modified by orography as the models were built. So these cases considered as successful. A combination of statistic and also time lag ensemble prediction in this system in this case is considered and successful on detecting 168 hours before the event. Thank you very much for your attention. Thank you.
Okay, so thank you for the presentation from Ms. Hanifa. Yeah, if any audience can have questions, just write down your questions on the chat box, and we will be discuss that at the end of the session. Okay, so we just go to the next presenter. It will be from Sam Hardy, John Medven from the University of Leeds, United Kingdom. It's Sam Hardy here.
Hey, Ronaldo.
Hi, Sam. Yeah.
I'll just share my screen 1 second.
Okay, sure. Okay, we can share video.
Okay, 1 sec. Yeah, that's cool. Hopefully you should be able to see these slides in a sec.
Okay, go ahead.
Thanks, Ronaldo. So good afternoon, everyone. Today I'm going to be talking about some work we're doing at the University of Leeds in the UK on the Borneo vortex as part of a larger scale project on high impact weather across Southeast Asia. So I know that the Borneo vortex may mean different things to different people. So I'm interested to hear what it means to all of you guys, maybe in the questions afterwards. But in the talk today, I'm going to be discussing this phenomenon based on literature that we've read. And what we mean by the Borneo vortex is a warm core tropical system on the synoptic scale, which organizes deep convection and heavy rainfall and is most intense in the lower 1 to 3 kilometers of the troposphere. And our motivations, our research questions to dig into the vortex mechanisms are kind of motivated by this idea of balance. So in the mid latitudes, we've got large scale balance flow dominates, kind of moving around troughs, ridges, and the jet stream and things like that. And this idea is also applicable in the subtropics and tropics to an extent. And we're using that idea to basically split the flow into balanced and unbalanced components using this approximation tool that I'll go into in the next slide that was written by the Met Office. And so we've got this tool, and then we want to determine whether the Borneo vortex is part of the balance flow or not. And we can also use the tool to investigate the role of specific processes such as diabatic heating on the vortex intensification. So the SGT semi-geotriptic tool I'll describe here, and I'll refer to this later on in the talk again. This is basically an extension of semi-geostrophic theory with friction included. So it's a three-way balance of forces, and it allows us to do two things. The first of them is to basically get back the 3D ageostrophic motion just from the pressure field alone. And then, as I said in the last slide, we can then attribute portions of this motion field to different processes such as diabatic heating. It takes global Met Office unified model data as input, as we'll see in the coming slides. And for more information, you can look at these two references down at the bottom here. So that's our model, which we'll return to. But our actual data is a single event from late October 2018, which in which a vortex moved westward through the South China Sea and then impacted Vietnam in the south. And basically, we identified this using Kevin Hodges' tracking algorithm, working at the University of Reading, where we track vorticity features in the 850 hectopascal vorticity in era interim reanalysis data. So that's what we're going to look at in the coming slides, this single case from October 2018. Before we get into the output from this tool and the Met-UM, just a quick look at the observations to show that looking at total precipitable water satellite imagery, we're actually able to see the vortex tracking westward as a region of enhanced moisture through the South China Sea, and then impacting southern Vietnam on the 22nd and 23rd of October. It's not always that visible, but this is a relatively simple way, at least in this case, of identifying the vortex track and position. It's also somewhat visible in GPM I-merge accumulated rainfall. So we see on the right here, we've highlighted the position of the vortex in the observations and the Met Office model, and it's less easy to see in terms of the rainfall than the moisture, but we do get a sense of some organization of the precip as it tracks towards the west across the South China Sea in both the model and the observations. So now returning to our research questions, the first one of these was whether or not the Borneo vortex is described by this SGT balance. So is it part of the large scale balance or not? And to answer the question, we have got plots here of relative vorticity at 1.3 kilometers, so just above the boundary layer that's shaded in these panels with wind vectors overlaid. If we first concentrate on the top two panels, this is the Met Office model data that we use as input for the SGT tool. we see the vortex shows up as a region of enhanced vorticity that moves slowly westward with time. So through the South China Sea into southern Vietnam at T plus 72. If we then compare with the SGT tool, so everything here is basically the large scale balance component of the flow, we see that it's able to pick up this region of vorticity that then moves westward. So we're obviously going to look more into the details, but this is a strong indication that on the large scale, even though there are differences between the top and the bottom panels, this tool, basically the vortex is part of the balance flow according to the output from this SGT tool. And if we look now a little bit more at the vertical structure, so we've kind of answered that first question. Our second question was, which physical processes are driving the intensification of the Borneo vortex? And we're answering that question, first of all, by looking at this vertical structure. So on the left, we've got these horizontal cross sections, and we've constructed vertical cross sections from north to south through the vortex at this time when it's kind of at close to peak intensity. So if we focus on the top right panel to start with, which is the zonal wind, we can see that first of all, we've marked the vortex center on with this V below the plot. We can see there's a nice dipole here of westerly winds in red to the south of the vortex, and then easterlies to the north. So we have a closed circulation that we can also see in this plot, which extends up to about 4 kilometers and is maximized in the lowest few kilometers, as we saw earlier in the literature. If we now look at the relative humidity, again, we can see there's a kind of a region of close to 100% relative humidity near the vortex center at 1.3 kilometers. And this is part of a larger scale region of saturated air close to this V between about 6 and 8 degrees that extends up from the boundary layer. So we have a closed circulation and we have saturated air in this region. So the last few slides are just using that second feature of the SGT tool that I mentioned, which is it allows us to partition or basically split the parts of the vertical velocity that are attributed to different physical processes such as diabatic heating. And we can see that in this panel plot here. So ignore the ageostrophic wind vectors, we won't have time to discuss these, and just concentrate on the shaded field, which is the vertical velocity. And you'll notice the main feature is this tropical storm to the east of the Philippines. We're not going to go into that today. The region we're interested in is this area just to the southwest of Vietnam, which is where we've seen already the Borneo vortex is located at this time. And we can see in the MET-UM output, we've got a region of upward motion, which is associated with the center of the vortex. And this is weaker in the SGT tool here on the top right, but it does pick up this signal of kind of probably weaker rising motion near the center of the vortex in association with that closed circulation that we saw in the previous cross-section slide. If we then partition this this vertical velocity here into the two main forces, so diabatic heating and geostrophic forcing, we find that it's all forced. So all of the red contours here are forced by the diabatic heating, none of them by the geostrophic forcing. So this shows us that all of the rising motion in the vortex vicinity, like near the center, is forced by this heating zone.
You have 2 minutes more.
Thanks, Nadi.
Okay.
So yeah, just to wrap up, we've taken a quick look at this single case study from late October of 2018 that brought heavy rainfall to southern Vietnam. We've shown that the vortex, the Borneo vortex, can be identified in satellite data, at least in this case. Not sure about more generally. The vortex circulation is described by this balance, SGT balance term, as we've seen, and we do have saturated ascent occurring in the center of the vortex, which results in latent heat release. And this last point of amplifying the circulation, we're still looking into. So this is ongoing work, but hopefully, yes, we've provided some indication of this system for you today. So thank you for your time. I'll take any questions afterward.
Okay, thank you, Sam, for the presentations. So, if there is any questions, just write it down on the chat box, and the presenters will answer it at the end of the session. Okay, so we just go to the next presenter. It will be Mr. Robbie Marsha from BMKG.
Yes, Pak Donaldi.
Yes, team is yours.
Can you hear me and my slide?
Yes, very clear, and I can see the slide as well.
Okay, good afternoon, everyone. I will present my short research about the Bayesian model averaging to improve prediction quality of SST in Nino 3.4 region. I am Robi Moharsha. Okay, this is my outline. We start with the introduction. We know that the ENSO is the phenomenon in equatorial Pacific, characterized by SST anomaly in Nino 3.4 region. Usually we use the threshold around 0.5 degrees Celsius. And so more accurate ENSO prediction is very essential for the Indonesian region because it's affecting rainfall in Indonesia. And in BMKG, we routinely monitoring the latest condition and predicting SST in the Nino 3.4 region for several months ahead. Were collected from ECMWF, GMA, BOM, and CPCNA. Many studies reveal that scale of SST ECMWF SIS4 or previous version of SIS5 is better than other models such as CFS 13.2. And recently, a study by Johnson also proved that prediction SST in 3.4 using SIS5 corrected or using bias correction has better skill than SIS4. We can see this is a reduced bias, higher correlation, and lower amplitude, lower RMSE. And what is the problem? Bias correction is the most popular statistical post-processing that has been used to improve the seasonal forecast model. However, several studies will report that DC cannot solving overconfident problem under dispersive like this one, or small variation but far from observation, and over dispersive or too large variation in the direct output of raw ensemble prediction such as SIS5. And unfortunately, in a study which report by Johnson et al. In 2019, no evaluation that show the ability of SIS5 probability prediction, in particular to predict probability of ENSO perfectly, separately such El Nino, La Nina, and Mistral. So this study aims to apply the statistical post-processing method as an alternative to correct the bias of model. The method, which known as the calibration technique, is able to quantify the uncertainty inside ensemble prediction by using probabilistic forecast. We use to data here, the model data we use the SIS5, we get the monthly average of SIS5 in Nino 3.4 region. We download the data in Copernicus Climate Change Service, CS3, from 93 until 2020, and we use the observation data from ER SST version 5. We can check the comparison about the ECMWF model with other model in WMO website. We propose the method we call as Bayesian model averaging. The Bayesian start with find the contribution of each member, which expressed is PDF posterior and weight. And then each posterior PDF and weight is generated in during the training window. For SST, we use the normal distribution to get the SST to get the PDF posterior, and then to obtain the BMA PDF predictive for time Tn+1, we need the information from T1 until Tn. For example, in here we use the 10 months training window with sequential training window. We conduct the training window with sequential method, The target month is shifting month by month. And the most important in here, the weight in our model we set in as 1/25 because the main source of ensemble member of SIS5 derived from the single model, which given random perturbation to generate several individual prediction. So it means the member ECMWF is exchangeable. To evaluation, we use the Pearson correlation, RMSE, proportion of correct to check the categorical accuracy. And in probabilistic prediction, we use Barrel score and ROC. The result, we start with the find the optimal training window. We find here the training window 160 months as the optimal window, with indicate by CRPS, the smallest CRPS. This means that the observed value is closest to the BMA PDF when using the training window 160. And then this is comparison of BMA PDF and spread row. For each target month, various BMA PDF is found both in density or curve height and the variance or the curve height. And in strong El Nino 2015, we get as an example, and strong La Nina in 2010. We can see BMA mean and BMA median are relatively closer to the observed value than raw mean for LT0, LT1, and LT2 in El Nino. But in strong El Nino event, the ability BMA similar with the raw model. So in this figure, this figure has converted to SST anomaly. By using SST anomaly, we can easily to identify the performance BMA and raw for each ENSO category. In general, we found that in LT0, spread row tends to narrow and far from the observed value, in particular during the El Nino and neutral. Meanwhile, in LT1, the spread row too wide, LT2 also too wide, even though it can cover the observed value for each ENSO categories. Too narrow and too wide, the spread row show the SIS5 rows suffer from overconfident problem. This is condition, the overconfident problem is a big common problem for ensemble prediction from GCM output. And our result next about the evaluation of the deterministic prediction, we can see in here the proportion of correct BMA accuracy is significantly can be seen in the first two lead times, while for lead time 2 until 6, BMA drop below the row. And then for the correlation, BMA and row very similar to the through observed pattern. We can see in the previous figure here the pattern is very similar. That's why the correlation is very high. And then from the RMSE, BMA mean and BMA median are better than raw mean in order to eliminating the bias. However, it's only valid for first 3 lead time. We can see in this figure. And then for evaluation for the probabilistic prediction of raw versus BMA, we can see BMA very superior to raw in predicting probability of El Nino and neutral condition for all the time. But for La Nina event, there is a slightly different between the BMA and raw. The BMA is superior to the raw model for lead time null only. And area under curve of ROC to describe how well the BMA or the raw in the discriminating ENSO per events occur. In general, both of BMA and raw, the ROC is more than 0.5. It means the BMA and raw has good skill to discriminate the event of El Nino, La Nina, and neutral. But interestingly, the probability of ENSO occurrence, which generated from the BMA PDF, looks very close to being perfect. We can see here the score is close to 1. This means that the BMA probabilistic prediction has higher confidence level than raw SIS5.
2 minutes more. Okay.
Our conclusion is, besides the bias correction method, BMA can be used as alternative post-processing to improve the quality of SST as one of the output of ensemble prediction system ACMWF seasonal forecast system SIS5. And second, the output of BMA deterministic prediction is highly recommended to be used as the SST Nino 3.4 index. From this study, it's also found that BMA is promising output for 2 or 3 months ahead. As probabilistic prediction of ENSO categories, BMA is superior than raw for all the time. And another advantage of BMA doesn't need the real-time forecast for target month. BMA only requires updating the information from the observation value. So we not need to waiting the real-time forecast of SIS5, which usually available for 8 and 10 days every month. Thank you. That's all my presentation.
Okay, thank you, Mr. Robi Maharsha, for the presentation. So we shall now go to the next presenter. It's Mr. Boni Septian. I think he's not in the room yet. We can just skip him, and then we go to the next presenter, Miss Destri Intan Shafitri from maybe STMKG. Miss Destri is already in the room.
Yes, sir. In here.
Okay. So time is yours.
Can you see my PPT now?
Yes.
Okay.
Okay.
Good afternoon. Let me introduce myself. I am Destri from Department of Meteorology, the School of Meteorology, Climatology, and Geophysics. Today, I want to present our research about 4-dimensional variational performance test with assimilation satellite and radar data, case study of a heavy rainfall Bengkulu on March 4, 2019. This is the outline today. First, introduction. The Bengkulu region is directly adjacent to the Indian Ocean with a varied topography that has frequent hydrometeorological disasters. It makes one of those cases included the 3 major hydrometeorological disasters in early 2019. Thus, this study uses the WRF to simulate heavy rain event in Bengkulu. WRF is one of the numerical weather models which can be forecast on a mesoscale, but there are some shortcomings in the initial conditions that can be improved by assimilation data. The assimilation system in WRF has some techniques in the process. One of them is 4D-FAR, which includes time integration for the distribution of observation data. Previous study has been carried out by Yi et al. Using TRMM and GPM satellite data on heavy rain events, and the results show that this technique can increase the accuracy of rainfall compared to non-assimilation. Then Mazzarella, using radar data on heavy rain events, and has the result that 4D-FAR can increase the prediction skill for high-intensity rain. This research is focused on the satellite and radar data using WRF model with 4D-FAR during a heavy rain event on 4th March 2019 in Bengkulu. And the aim of this study is to see the performance of each WRF model result before and after the assimilation was carried out using satellite and radar data with 4D-FAR techniques spatially and temporally. Next, data and WRF model. This research uses HPC by LIPI and WRF version 4.1.2. For observational, rainfall observed data from AWS and ARG, and then GSMAP rainfall accumulation data which processed with NCL. For the assimilation, using GFS and CV5 data as background error, radiation data from NOAA satellite, and lastly, reflectivity and radar velocity data from Bengkulu Weather Radar that processed with Python and RStudio. The methods. This domain is applied with downscaling and nesting technique with the resolutions of 1 to 3. On these processes, we use this configuration, and post-processing, we uses NCL to get the scans. Then for verification, this research uses the Aibo method as spatial verified, and for temporal, it uses statistical verification, which is correlation coefficient and RMSE, then with discrete, which is bias, accuracy, and FAR. For the results and discussions, they divided into 2 groups. First, spatial analysis of daily rainfall distribution. In GSMAP, the distribution of daily rainfall occurs almost along Bengkulu mainland to the ocean with maximum value around the ocean of southeast. However, the rainfall produced by non-DA is distributed over the research domain. This scheme has not been able to detect the presence of high rainfall in the Bengkulu Ocean. Compared to GSMAP, DASAT can detect high rainfall in the Bengkulu Ocean with a value of 75 to 85 millimeter per day. And then, compared to the other schemes, DARAT has succeeded in detecting the absence of rain pattern in the central to northeastern part of Bengkulu. However, this scheme is not able to detect the presence of high rainfall in the ocean. And overall, DARAT can produce rainfall pattern that is closest to GSMAP and improving the rainfall in mainland, while DASAT can improve rainfall in parts of ocean. Next, temporal analysis for quality of model output performance. This is time series graphics. And based on the first point, DARAT is unable to predict the occurrence of rain at this point because it is in the cone of silence radar area. However, DASAT has a value that is closest to the accumulated rainfall of the observed data with a value 15.68 millimeter, whilst non-DA is successful in predicting the start time of rain at 11 UTC. And this graph shows that DASAT has the closest accumulated rainfall value to observation with a number of 21.44 millimeter, whilst DASAT and DARAT can predict to the start time of rain event at 12 UTC. At this point, non-DA has the closest accumulated rainfall to the observation of 22.98 millimeter. For the start time of the rain event at 9 UTC, DARAT can detect it successfully. Then this graphic shows that DASAT can predict the accumulated rainfall closest to the observation of 26.66 millimeter. And the last observation point, non-DA is unable to predict the rainfall because but DASAT successfully has the closest accumulated rainfall of observation with 15.31 millimeter. In statistical verification, DASAT and DARAT can succeed in reducing the error value of non-DA. This is in line with the result of SUS research, which states that the use of remote sensing assimilation data with 4D can reduce the error value of the model results. And the correlation value between the model results shows that each scheme is not capable of predicting fluctuations in rainfall correctly. However, among those schemes, DARAT has the best RMSE value and correlation. Next, discrete verification. The best bias value is generated by DARAT with a value of 1.0583. Then the highest rainfall event prediction accuracy value is also generated by DARAT with a value of 0.825 followed by DASAT. This is in line with the research of Pan et al., who stated that the assimilation of remote sensing data using 4D technique can increase the accuracy value of the WRF model. Nonetheless, the lowest par is generated by DASAT with a value of 0.5962. Based on those verification techniques, each of DASAT and DARAT scheme has different influence in improving model performance. From time series, DASAT can detect the presence of rain event at each observation point because the maximum range on data satellite can cover the entire domain. Meanwhile, DARAT can improve the initial rainfall occurrence time in the model after assimilation. In statistical verification, both can reduce the error value and increase correlation. And last, in verification discrete, DARAT has the best bias value and the highest accuracy value. Meanwhile, DASAT has the lowest par value. The ability of these two data assimilations can improve model performance in different ways because 4D can accommodate time integration. Thus, the density of data assimilation in 4D greatly affects the model performance. And the conclusions. Especially, DARAT can approximate the distribution pattern of the daily observed rainfall and improve the rain events along Bengkulu mainland, whilst DASAT can improve the rain events in Bengkulu ocean area. Temporarily, DASAT can improve the accumulated rainfall value from the model and produce the lowest par value of 0.5962, whilst DARAT can predict the onset of rain events, reduce the error value, which is 0.8972 millimeter, and increase the correlation value of 0.2737. It also produces the lowest bias value and the highest accuracy of 1.0583 and 82.5% respectively. And for suggestion, using 4D requires a large RAM capacity. Then CP7 as background error data can also maximize the radar assimilation data. And lastly, further research is needed by using combined of satellite and radar data. Thank you so much for your attention.
Okay, thank you for the presentation from Ms. Destri Intan Safitri. And we already see some questions on the chat box. So for the presenters, please to prepare the answer to that. And we have two more actually, but it seems like they didn't show up in the meeting. So I just have an announcement from the committee that there will be additional presenter for this session. It will be from Ms. Halima Salsabila from the IPB University with the title of Estimation of Spatial Distribution of Maximum PM10 and PM2.5 concentration in Bandung City using the WRF-CAM model. So I think I can just go ahead to Miss Halima. Are you ready?
Yes, yes.
Yes, so time is yours.
Okay. Wait. Did the presentation has show?
Not yet.
Oh, not yet. What about now?
Still no.
Still not yet. Wait. Wait. Now?
Yes. Yes, we can see now.
Okay. Yeah. Before I begin my presentation, I would like to thank to the committee that have the time to presentation. So today I will present my presentation about estimation of spatial distribution of maximum PM10 and PM2.5 concentration in Bandung City and surrounding country using WFK model. So the first question is, why did I took this topic? Well, as we know, Bandung is one of big city in Indonesia with high activity in industrial and transportation that will increase the air pollution emission and adversely affect the public health. Based on that matter, monitoring of air pollutant emission is urgently needed to predict the dispersion of air pollutant and to analyze which locations are vulnerable to be maximum exposed of pollutant. But the problem is field monitoring to predict the pollutant concentration is need much time and highly cost. But model could help for this. And model research forecasting chemistry or WRF-CAM could use for analyze or predict the air pollution dispersion. So this is my objective of this research. First, to predict the direction of air pollutant dispersion in Bandung City, and second, to estimation which locations are vulnerable to maximum exposure of PM10 and PM2.5. And the methodology is, first, I download the meteorology data and global emission data from the national and atmospheric website. And after I download it, so I can running the model. So from the output of the model, that we can see from figure 3 that PM10 that the which has been analyzed visually so that the distribution of PM10 in Bandung City is spread out following the local wind direction. And this pattern is spread mostly to the west, northwest, and north following the wind direction. And based on the model output, the maximum concentration of PM10 in July and October is located in west and southwest Bandung area, which are close to Padarorang Industrial area in West Bandung Regency and several gates which provide access to come and out of Bandung City. And as we know, industrial activities, transportation, and other activity play a major role in increasing the emission pollutant into the air, which cause air pollution. And from figure 4, also we can see that PM 2.5 has a dispersion pattern that is almost the same as the particulate or PM10. It's because PM 2.5 has almost the same characteristic as PM10, but has a smaller particular size. And the dispersion of PM 2.5 is partly spread mostly to the east, to the west, and southeast, following the wind direction. And from the figure 5, we can also see that the diurnal fluctuation pattern of PM10 from the aircraft cam model output in July and October at Bandung Geophysics Station and Lapan Observation Station, so that the particulate concentration is increasing at night and reach the maximum value in early morning, then decrease during the day, and the maximum concentration occur around 3 until 5 p.m. And increasing concentration of PM10 at night and early morning occurred due to stable atmospheric conditions, so that pollutants tend to be trapped and accumulate on the surface. And overall, from the model output that we can also see from figure 6 and 7, that overall concentration of PM10 in Bandung City is still below the national ambient air quality standard PM10 in 24 hours, which is 150 microgram per cubic meter. And almost the same with PM10, the diurnal fluctuation of PM 2.5 also increasing at night and reach the maximum value in early morning and then decrease during the day. And the maximum value occur around 3 until 5 p.m. And overall, the PM 2.5 concentration in Bandung during the raining period in July and October in 2018 is still below the national the ambient air quality standard PM 2.5 in 24 hours, which is 65 microgram per cubic meter. And the result of the correlation analysis of the meteorological pattern, which is wind speed and air temperature from the model output, to the observation data at Bandung Geophysical Station and Lapan Observation Station. So very good and significant correlation in July, but not good enough in October. And the last, according to the output model, almost all the districts in Bandung City have the potential to be exposed to the maximum concentration of PM10 and PM2.5. And the model showed that in July 2018, there were 24 sub-districts that had the potential to be exposed to the maximum PM10 and concentration, and there were 24 sub-districts that had the potential to be exposed to the maximum concentration of PM2.5, and
You
meanwhile
have 2
in
minutes left.
Meanwhile, in October 2018, there were 23 sub-districts that have the potential to be exposed to the maximum concentration of PM2.5, PM10, and 18 sub-districts that had the potential to be exposed to the maximum PM2.5 with different frequency. And we can also conclude that Bandung Kulon and Babakan Ciparai were the most polluted sub-district by PM10 and PM2.5 either in July or October. And the conclusion is dispersion pattern of PM10 and PM2.5 in Bandung is spread mostly to the west, northwest, and north following the wind direction. And second, almost every district in Bandung is to maximum exposure and 10 and line of it in Cicendo on July 3rd, 2018 at 5 p.m. with concentration is 570 microgram per cubic meter, and the high concentration of PM2.5 during the running period on July in October is located on Bandung Kulon and Babakan Ciparai, where its concentration is at 191 microgram per cubic meter on July and 209 microgram per cubic meter on October in both locations. So that's all for me. Thank you for attention.
Okay, thank you, Ms. Halima, for the presentation. I think it's precisely like 10 minutes. Okay, so I think that was the last presenter in the session. So before we go to the convener for their comments and maybe questions, I will ask from the first presenter to answer the questions that has been posted on the chat box. Maybe first from Usman. Yeah, can you even if you write it on the chat box, just try to explain more about the answer of the questions that's been given in the chat box. Is Usman is still here? Or Anistia Malinda? Okay, so maybe we can just go to Mr. Wendy Arjupa.
Yep, I'm
please.
here. Yep.
Yeah, you have I think several questions. Maybe you can explain a little bit.
Yes, I found one question for me about the how long we can the prediction by using the RDCA. This only for 1 hour because we match up the Himawari data with the lightning data in 1 hour. So we just can predict for 1 hour ahead. Then we use 7 bands of Himawari data because those bands, we use specific for the cloud, not for SO2, not for FOX, or for the weather vapor because Himawari has like 16 bands with it used for specific purpose. That's why we only use 7 bands. Is there any other question for me, Pak Donald?
I think that's all for now.
Okay,
Okay,
thank you.
thank you for the response.
Thank you.
And maybe next from Miss Hanifa Ramadhani. I think the question, why the all percentile based on this model have almost the same pattern?
Okay, thank you for the question. The percentile have almost the same pattern because we know that the model is obviously built by the topography area, orography area, or so far it's just how the base on the real itself, and then we know that in the nearby area have almost the same orographic condition, so that's why they have a same pattern. We also know that they also have a higher threshold because the model itself is built how they condition in real. Meanwhile, as the coastal area, such as northern Jakarta, we know that the precipitation in coastal area are most likely modified by the wind, such as sea breeze. So if we predicted around the mountainous area by using models, it will be having a better result and also likely have the same pattern. Thank you.
Okay, thank you for the answer and the response to the questions. Next, I think to Miss Destri. I think there is three questions.
Okay,
Maybe you can read it on the chat box.
Okay. For the first question to Mr. Robbie, for microphysics parameterization scheme, we used Lin et al. And the reason because this is in an academical research. So what we did, just believing in previous statements that used by Handoyo, published in 2015, and fortunately has the same ROA, which is in Bengkulu. And for the next question to Mr. Arayan, we use why didn't you choose? Okay, because as long as I concerned, there is no special data available for rain that is provided by BMKG. So we use the GS map data, which has an accuracy value of 82.5% for the maritime continent of Indonesia, based on the research of Faturayan. And the last question, we use radiation data from the Advanced Microwave Sounding Unit A, or MSU-A, and microwave humidity sonder, or MHS, on the NOAA satellite 15 to 19 satellite. Thank you.
Okay, thank you for the response. So the other question is, why is there any way to combine the DA-RAD and DA-SAT? I think that is one of their research, their future works, I think, on the last slide. And maybe to Usman, do you want to respond to the questions about the term of optimum prediction time and what are the benefits for the petroleum mining industry?
Okay, thank you for the session. Okay, telephone exponent is the indicating how the system is sensitive with the initial condition. So an initial cost also can be determined of the accuracy of optimal prediction. And there is no definite accuracy value to determine the ability. It is so just when the prediction is done beyond of the prediction time, the predictions are useless or not good enough. And the second is the benefit of this risk for the petroleum industry. Maybe they have better strategy for prepare the detection and mitigation action due to the rainfall appearance. For example, if they're planning for long-term mining activities that require rainfall prediction information, they should pay attention to predictability times to minimize loss due to unpredictable rainfall. Thank you.
Okay, thank you for the response. Okay, I think next we can just go to the conveners for giving their comments or maybe suggestion, thoughts, and even questions to the presenters material for today. So I give time to maybe the first one is Dr. Ahmad Faki. If you have any comments, please, and we can continue to Professor Edwin after that. Please, Dr. Faki.
Thank you very much, Dr. Donaldi. Assalamualaikum warahmatullahi wabarakatuh. Yes, I have made some notes regarding not all the presenters, but only several presenters. First one for the Usmanura Anistia. Regarding the presentation, I found that there's some unclear conclusion regarding the optimum time, especially regarding the 5 day and 10 days, and it's a bit difficult to understand what is the meaning, like 10 times, 18 times, and 16 times. And the other thing is related to the since this is observation-based data, and how would you consider in relation to the use of weather forecasts based on the dynamic or numerical models? As we know that the observation that the forecast that we usually use in the operational is not only based on the observation, but also use the modeling. And what is how do you link this the result of your study into this operational aspect? I think that would be the question that for me is still unclear. And the other thing is related to for the next presenter, Wendy. I saw that you comparing two approach using the RDCA and the BTD. But what I found in your presentation, you only show the RDCA mostly. So comparing to the two method, maybe you can give some insight in terms of, you said that you only can predict for the 1 hour lead time. Based on those two approach, which one has the longest lead time in terms of their best predictive skills? Because since your result is showing that the RDC is better than the BTD, but how about the lead time between those two? And for the Hanifa, you're using a time-like ensemble analysis, and when using this kind of approach, there is a possibility you potentially compare or use the data which has different predictive skill, because as we know in weather forecast, the different lead time may produce the longest lead time you may have lower predictive skill. And since you combine different lead time in your ensemble prediction, there's a possibility that you have inconsistent operation between one and the other, because there's two different type or different types of predictive skill between the output of the models. And the other thing is that evaluation that you show, it's mostly subjective in my perspective because you only show based on the visualization. I think it's better to also use some measured metrics that can measure the accuracy or the comparison between in every grades of the in spatial data of the of every grade point of your spatial data. So we can show, because in weather predictions, as we know, different locations may have different, but if you show is in spatial in general, maybe it will be look well, good, good in visual, but in fact, different location may produce like a very different result. And the weather forecast mostly use like location-based to generate or to get the data. User will use the it's their location to generate the data, to get the data. So I think it's also my point is use the more specific metrics to do the evaluation. And for the SAMHARD, since your analysis is to your study is to use to evaluate the performance of the models in providing or simulating the Borneo cortex. Maybe my question will be how consistent the model can produce well the Borneo cortex in terms when you consider the evaluation using many sampling time. Whether it will be consistent based on the result, or it will have a like inconsistency in that. For Robbie, did you conduct evaluation for each individual and sample member, and how do you consider also the updates from the issue time of the forecast data? Because as you know, in seasonal forecast there will be update every month. And it will produce different forecast data for for the same lead time. I think that's all, Donaldi. My comments because for the I don't have question for Destry as well as for the Halima. Thank you.
Okay, thank you, Dr. Faki, for your response and maybe some input for the presenters. And the second one is second convener is from Professor Edwin. Are you in the you are in the room right now? I think he's not on the room right now. So so I think in the while we're waiting for Prof. Edwin to give maybe his comment on our presentation today, if maybe from Sam or Robbie, do you have any comments for the input from the Dr. Faki?
Yes, Pak.
Yes, Robbie, please.
Yes, thank you for a comment from Dr. Faki. We also concerned about the update. I will show my last slide. Actually, I prepare one slide to explain why I say that BMA have advantage than bias correction. So in bias correction, we do the waiting for the real-time forecast for the target month, and the real-time forecast will be corrected by using the correction factor. But in a Bayesian model, we not need the real-time forecast. Because the Bayesian model is generated by using the update of observation only, by using the last real-time forecast, the last month. We also can generate the predictive of BMA. By using this predictive, we can estimate the mean as the probabilistic forecast or the median, and we also can generate the probabilistic forecast from the PDF curve. And also in sample member in Bayesian, we not need to consider for every single member, because in this case the member is quantified with the same weights as I mentioned before in my presentation. So the main purpose of BMA to generate the PDF curve only. Okay, thank you. This is my explanation.
Mr. Robbie for the response. So for Sam, maybe before you give the response, I would like to give time to Prof. Edwin for giving the comments, maybe suggestion or questions to the presenters. Please, Prof. Edwin.
Thank you very much, Mr. Moderator. I think I just see all the presenter and then I have to go out for a while. This is a modeling group. I'm very happy that you make a very much progress on the modeling system. I like the second ladies for the English speaking. I don't know, forget the name of the second ladies.
It's Miss Hanifa.
Yeah, I think her English very good. Okay. Usually in Indonesia there is a problem of seasonality, especially for prediction. So if you're talking about prediction as just said by Mr. Robbie, I think for example, for the El Nino La Nina prediction, you must take care of the seasonality. This is the common problem. I think you must mention that without that it is not possible, I think, to bring that in international level. For Mr. Wendy, I really like your work. I really admire your work, not only this today, but I think since your lifetime. I know you come from Bukit Tabang as also the work for Pak Donaldi as well. So if you use satellite for the next generation for weather prediction, I think you will face some problem with that because the satellite has the scale of the temporal resolution is getting very good now. It is like 10 minutes temporal resolution, but the spatial resolution stay almost the same. Only 250 degree. So this is the problem. I think you must also look at the notice of the difference between higher resolution. So, for example, you can make some analysis for the higher, like higher increase of the cloud height changes and the small increase of cloud changes, whether they are the same or not. This is the next phase you want to do with your work, and then with the first presentation about the Bojonegoro, I think this is you mentioned about too much of the theory. I think you must. This is only 10 minutes presentation. You just mentioned the result and what is the significance of your expectation. This is you must very clear on that, and then you come up with the conclusion. So, but anyway, I think the all presentation is very good, very nice, and I also welcome you in your presentation because I have to make my judgment on who's the best presentation. So I think all of you make a very good presentation with a small improvement if possible. Thank you very much, everybody. Okay, back to you, Donald.
Thank you, Edwin, for the comments and inputs for the presenters. I think all the inputs that been given by the companies can be consideration to improve the full paper if there is any review in the before we being submitted. Okay, and then maybe there is a question from Sam Hardy. Maybe if I not mistaken, I think the question from Prof. Faki is about how consistent is the model to simulate the Borneo vortex. So maybe if you want to give some response to that.
Yeah, so thank you for the question. It's a very good question. We're currently investigating this question at the moment because we've only been able to look at one case in detail. We're using the tool also to look at equatorial waves and cold surges with a couple of other cases from November and December of 2018. And the results look encouraging to us, but we haven't gone into detail, so we can't say for certain whether this is the model is able to generally resolve the Borneo vortex, but we are looking into this for sure.
Okay, so thank you for the answer, and I think all of us has been finished for the presentation, and the conveners has given the comments, and I think we are at the end of our session. I think I can just close this meeting session. And is there any question? Maybe if maybe one or two more questions, just short. Okay, so it seems there is no more questions, and we are now like on the 5:40 p.m. now. I think I just want to thanks to all the presenters for the very interesting presentation, and also thanks to the convener for the comments and the inputs. And I hope this can increase our knowledge about the modeling, and I hope we can join again tomorrow for the next session, plenary, and also the parallel sessions. So again, from me as a moderator of this session, thank you again for your contribution and your participation, and see you on the next meeting. Thank you. Bye-bye, everyone.
Thank you.
Thank you, Pak Donaldi.
Thank you semua. Pak Wendy.
Thank you,
Thank you, Pak Rabi.
Terima kasih
Makasih, Pak
semuanya.
Faki.
Terima kasih.
Yuk.